Hello, everyone. I'm Maliha Ashraf. I'm a postdoctoral researcher at the Rainbow Research Group, which studies computer graphics and human interaction. So today I'll be studying about human vision. Why study it? How can we model it? What can we learn from it to improve human and machine interaction, basically? So first, I will give a brief introduction of why study human vision at all. Is it worthwhile for us in computer science or tech to study it? And then, are there any specific methodologies that we can use to more efficiently extract this information? What are there any research areas that deal with this? How to measure it? What are the techniques? And throughout my talk, I'll also show you some applications of where we use this kind of information in technology. So, starting with the question, why study human vision at all? So, while humans receive a lot of information constantly from our environment, right? Sights, sound, smell, but about 80% of this is there a pointer? I was trying to get the laser pointer to work.
I don't know to get this back. Hold on. Oh, there we go.
Sorry. Okay, thank you.
Is that working? Let me just hide this.
Okay, the pointer is working now.
Good. Let me just hide this again. Okay. Is that working okay?
Yeah, thank you. Yeah, so from all the information that we receive constantly from the environment, about 80% of this is visual. And then we are evolved in such a way that a large portion of our brain
It's okay. Try that again.
Okay, now it's
Is that working?
right. So our brain is evolved in such a way that a large portion of it is dealing with the constant onslaught of visual information that we are receiving. So once the light or visual information enter the eye, then it goes through many different stages of processing in the retina, in the optic nerve, in visual cortex, and many different areas of the brain. But in perception research, we don't really care about what exactly is happening at each of the stages. That's more hardcore visual neuroscience. What we are interested in is getting the overall response. So if we show something in specific condition, what would be the response? Would we see it? Would we not see it? How well would we see it, etc. And then once we know all this, once we have that knowledge, we can use it to improve technology or define constraints of technology or to improve human-machine interaction. And one such application I'll just show you, it's called foveated rendering. It's a concept used in virtual reality and augmented reality. I don't know how much you're familiar with it, but if you have used such headsets, they have quite a wide field of view. So there's something that you're paying attention to at the moment, which is in the center of your visual field, but there is still a lot of information in the periphery. But when we are looking at, but when something is in the center of a visual field, we are not really sensitive to what's happening in the periphery. So there's no point in making all of this high resolution. For example, if you're looking at this red backpack here, this would be the center of your visual field or fovea, but everything around here, you will not be really sensitive to. So there's no point in wasting resources to make it very high resolution. So if you compare it with the original image, this was the full resolution image, then we can massively reduce the resolution here to save a lot of computational bandwidth, right? But this will require the knowledge of how exactly the sensitivity is changing from here to here to here to here, and for different colors and all that. So if we know that, we can do such things, right? So this is one such example of how we can leverage human vision knowledge. And how do we measure it, right? So this area of research is called visual psychophysics, and it deals with just measuring the response of human visual system to many different kinds of stimuli. And the basic idea is that we have human participants, we show them different things, we respond to it, we record it. So a very simple example would be we showed two different patterns and we'll ask them which one of these has higher contrast. And then they will say left or right, and we'll record them. And then we'll do many iterations or hours of these kinds of experiments. We'll do many different combinations, different, I don't know, light levels, different flicker rates, whatever we want to measure. And then if we select the combinations of these very carefully, we'll be able to see exactly what will be the limit where the difference between these contrasts will not be perceptible anymore. Will it change at different brightness level? Will it change for different colors, etc.? And so this wealth of information can then be used to build computational models of human vision, which we can use to interpolate or extrapolate in between, even in between the measurements that we recorded. And one such model, I'll just show you, we published it last year. So here you'll see a pattern which is getting brighter or darker. So this was like one of the images or one of the conditions that we have used. And on your left, on your right, you'll see a curve which is going up or down. And you'll see that when this image is getting lighter, the curve is going up. When the image is getting darker, the curve is going down. Essentially, what it's telling you is when the environment is brighter, you're more sensitive, or it's easier to see. When the environment is darker, it's harder to see. So we know that qualitatively, but this model will exactly quantify it. So you will know exactly if you change the light by 10%, how much the sensitivity will be changed in light. And you can do it for different spatial frequencies, so like for text or like more bigger objects, etc. So yeah, this is an example of such a model. And then another aspect of this model was we measured if the stimulus is in the center versus in the periphery, exactly how much, by what quantity will the sensitivity change. So when the stimulus is in the center, the curve is going up, or we are becoming more sensitive. And when the stimulus is moving further in the periphery, the sensitivity is going down. And I showed you the example, which basically uses this kind of information where we rendered the peripheral objects with much lower resolution. So this is the kind of information that we would use to do that or for such an application. Another such application that we worked on last year is called visual difference predictor. So let's say you have an image and then you compressed it. So image compression is used to reduce the file size, or if you have limited bandwidth over the internet, and you want to basically reduce the file size to make it easier to transmit. Here, this is an exaggerated example of a process called chroma subsampling. And what we do is reduce the color information in the image. So we have done that, but then we built a model which uses human visual system to predict what are the areas where humans will be able to see the difference, and so without any human intervention. So we use previous human knowledge, but then this wasn't done by actual human person, but rather this metric could predict, okay, this is the area where humans will be able to see the difference in quality in this area and this area. And so we basically built an automated tool which used the knowledge of the human visual system to simulate our perception. And we also did a small project last year where we measured the resolution of the human eye. And so it was basically for display manufacturers. We hear the terms 4K, 8K, Full HD, etc., which are used to characterize device pixel resolution. So this is like a photo of one of our displays. Each of these units of the green, red, white strips is 1 pixel. And the number of these pixels, or the density of these pixels, need to match the human resolution if we want to make the perfect display, right? So it needs to be at least matching the human display resolution. We could exceed it, but it will be a waste of resource. So we basically, when we increase the resolution, there is an increase in perceptual quality, but up to a certain point. If we go beyond that, there is no point because we won't be able to perceive it and it will just be a waste of resources. So what we want to do is exactly pin down what is the limit, what is the minimum limit that we require if we want to make the best display, but what is the upper limit where we won't be able to see any further increment in quality. And to do that, we built this display rig. So a monitor was mounted on a slider and moving this back and forth. So the observers were here. Moving the monitor back and forth changes the effective resolution, which enters the eye. And then basically we showed the observers different stimuli, and they said whether they could see it or not. And we did that from 8 different conditions. So we had 18 observers. Each of them did 3 hours of such experiments. So it is a time-consuming process and takes patience, but we get a lot of data. And using such data, we managed to build this kind of model. So here we managed to find the relationship or build a model which showed us for what viewing distance, what will be the minimum pixel resolution per inch we would need, where we could not be able to perceive the difference in quality. So yellow is below the human perception limit and blue is above the human perception limit. So here we benchmarked some devices, for example, a Samsung device. Using this, you can see that if the viewing distance is less than 1 meter, then humans would be able to see display artifacts. But if it's above 1 meter, we won't be able to see them. So this was benchmarking, but then you could also use it to build future devices. For example, if you are a display manufacturer and you want to build a brand new device, which needs to be viewed at 0.4 meter, you can see that, you would at least need a pixel, a PPI of 300. So you would obviously do your own cost benefit analysis, but this model could guide you what will be a good resolution, which is good for the human eye. So to summarize, studying human vision can give us a lot of knowledge about the perceptual limits. We can use this knowledge then to optimize the design of different human machine devices. Apart from hardware, we can also optimize different algorithm pipelines such as image and video compression, or we can build metrics which can do this automatically. And then you can also, one aspect of this research is also to customize the devices for specific subsets of vision. For example, older population or color deficient population or people with specific disease like glaucoma, etc. But then the process will be the same, but you will have to, very carefully isolate specific populations. So thank you very much. And Professor Abhal Mantuk and Alex Shapiro have been the main collaborators of this research, and the previous iteration of this work have also received funding from EPSRC and ERC apart from Nigeria. Thank you.